Okay, chapter 12 is electromagnetic induction. The first portion is about induced electromotive force, how like EMF is induced in a conductor moving in a magnetic field. Second part is about alternating current, and the third part is about transformers and transmission of electrical power. So let's take the first part, induced EMF. So we mentioned that any kind of a moving charge has a magnetic field around it. So therefore, if we have a conductor moving in a magnetic field, the moving conductor will produce its own magnetic field and interact with the magnetic field that it is in, and therefore there will be a force on the electrons in the conductor, and when the electrons move across a conductor and accumulate at the ends, there's a potential difference developed across the ends of the conductor. Okay, now you should know that you can actually derive the direction of the force of the induced current. So we always talk about the induced EMF. So when the conductor moves across a magnetic field, there will be an EMF developed, and if this conductor was connected in a circuit, the direction of the induced current can be determined using the right hand rule. So in the right hand rule, just like the left hand rule, your forefinger is magnetic field, just like the left hand rule, and the middle finger is the direction of the induced current, and the thumb, instead of force on the left hand, on the right hand it signifies the direction of motion. So if this is the direction in which a conductor is moving in a magnetic field placed like this, so again it's at right angles, there will be a force in the third direction like that. Okay, so you can use your right hand rule to determine the direction of the force. This is called Fleming's right hand rule, by the way. Now let's say I have a magnetic field placed into the plane of the paper over here, and there is a conductor of length L, okay, being moved at a velocity v like that. So again, if I use my right hand rule, the direction of the field is inwards, the direction of the motion is downwards, so there will be a force towards the right on the electrons within this conductor. So the electrons will basically accumulate at one end, and there will be a charge developed across the end. So firstly, the magnetic force is given by BeV. Okay, when we are talking about each electron, so each electron will experience this much force, and now the charge developed across the ends is going to create electrical force. Okay, eventually the EMF becomes large enough to balance the magnetic force, and the electrons stop moving. Okay, when this happens, this force will be equal to the electrical force given by the charge of electron multiplied by the strength of the electric field. Okay, now if there is a potential difference developed across the ends here, let's call the potential difference E, because we are talking about EMF. So this will be given by the electric field multiplied by the length of the conductor. Why? Because this is the relationship between the electric field strength and the potential difference across the length of an electric field. Okay, so if I substitute this value over here, so I'll get, this implies, from both of these we can get that the EMF induced is equal to BLV. Okay, and this is for one particular conducting wire. Now if the conducting wire was a series of coils, okay, you would have to add up the magnetic field n times when the number of coils is n. So in that case, the EMF induced across the ends of a conductor moving in a magnetic field B of length L and moving at a velocity v would be NBLV. Okay, next is defining magnetic flux and magnetic flux linkage. So when we have, for example, a conductor of area A, cross-sectional area A, placed in a magnetic field, okay, so B is the magnetic field strength, okay, and it is also called the magnetic flux density. Okay, so basically telling us how dense are the magnetic field lines over here. Magnetic flux would then be the density multiplied by the cross-sectional area, which is perpendicular to the magnetic field. So if this area is, for example, at an angle theta over here, we would only have to take the perpendicular component here. Since this is the angle from the normal, we would have to consider the flux. This is the symbol for flux. Flux will be given by the flux density multiplied by the perpendicular component of the cross-sectional area. Okay, so we have VA cos theta. So this cos theta might be a sin theta depending on whether this is an angle from the normal or an angle from the horizontal. Okay, so the students need to take that into consideration. Again, if I had a series of coils, I will have to add up the flux, and in that case, adding up the flux, the number of times that as many as the number of coils would be NBA cos theta. In this case, this symbol is called the flux linkage. Okay, so why is it called flux linkage? Because the magnetic flux from each coil links together to form a stronger magnetic field. Okay, so again, the flux will be stronger if there are more coils, if there is a greater strength of the magnetic field, and if there is a larger area. So basically, the area can be large and also kept normal to the magnetic field, and that will also make the amount of flux linkage larger. Okay, so now from here we have the strength of the EMF to be BLV. Okay, now again, if we have a magnetic field into the plane of the paper, and we have a conductor of length L, okay, and it's moving downwards. So it's moving downwards with a velocity v. So in 1 second, this conductor will sweep this much area, right? Okay, so this, in 1 second, it's going to sweep area which has length v, because it's moving at v meters per second. Okay, so this is the position of the wire 1 second later. It's moving in this direction. So now, since it has moved this much, the area swept by the wire is L times v. So that's the area. So v is L times d over t, right? Or rather, L times the change in distance over change in time. L times change in distance, like we can see here, is the area or the change in area with change in time. So now, since LV is this, we can substitute this in the formation of EMF over here, and we get what we get now is that the EMF, or the magnitude of the EMF, is equal to B times delta A over delta L. Okay, B times delta A can also be written as change in BA over change in T. Okay, sorry, this is T. So therefore, this is the change from what we just wrote right now. There's the change in flux over the change in time. So this is for a single coil. If, for example, we have a series of coils, so again we will have the magnitude of the EMF equal to N times the change in flux over the change in time, which is basically N times the rate of change of flux linkage. So this entire thing is basically the rate of change of flux linkage. So the magnitude of EMF is proportional to the rate of change of flux linkage. This here is called Faraday's law. Okay. Now, why are we talking about the magnitude? Because if we remove the magnitude sign, okay, if we remove the magnitude sign, then what we will get is a negative sign over here. Why? Because this is explained by Lenz's law. Okay, Lenz's law states that the direction of the induced EMF is in such a direction such that the current it causes to flow opposes the change producing it. So the EMF will always cause a change which will oppose the change producing it. What that means is, whenever a conductor is moving across a magnetic field, it is going to feel a resistive force. Okay, so the EMF will produce the EMF will cause a current to flow through the conductor, and since there is a current flowing through it, there will be a force on it, and that force will be in the opposite direction to the direction of motion. Okay, so this can also be seen from your left hand rules and right hand rule. If you align the B field and the direction of current, you will see that the direction of motion is opposite to the force that will act on this conductor. Okay. Okay, so that covers magnetic flux linkage and Faraday's law, Lenz's law. Now Lenz's law is explained a bit more on page 6, whereby they're bringing a magnet towards a solenoid and seeing how the current is induced in the solenoid. So you should know that if the magnet's north pole is being brought towards a solenoid, the solenoid would develop a north pole as well in order to repel this magnet. Okay, so again the EMF produced will be in such a direction such that the current it produces is opposing the change producing it. So if I take the north pole away, there will be a south pole there to try and attract the north pole back. So this is explained on page 6, and it relates to the law of conservation of energy, and that's why this Lenz's law came about. Following this, 12.1.6 is simply solving some induction problems using the formula that we've derived over here. And yep, after this we will move on to alternating current in 12.2.